All right, I think that we can start. So welcome to the Warren Lecture, special edition. But because we have also a lot of people online, because it's also a joint seminar for the Center of Geoprocesses in Mineral Carbon Storage. So it's really my pleasure to introduce Dr. Mengsu Hu. She's a staff scientist at the Lawrence Berkeley National Lab. And I'm going to say a few words about her journey, academic journey. So she has a bachelor degree from China University of Mining and Technology in civil engineering, and then from a PhD in geotechnical engineering with Ohio University in Nanjing. So she started at that time this long-running association with Lawrence Berkeley National Lab because she was doing a graduate study. She was a visiting student of the lab. And after when she obtained her PhD degree, she was hired as a postdoc at Lawrence Livermore. And then she stayed there, she climbed the rank, and actually she's now a staff scientist, as I said, which is quite remarkable because to become a staff scientist in the national laboratory, you need to have an international reputation, and you need to also to be able to have an independently funded research program. So that's quite remarkable, because especially that was so fast after she obtained her PhD. So her field is computational geosciences. Now she's working on understanding coupled processes, thermal, mechanical, hydraulic, chemical, using numerical modeling and also a machine learning technique. And she applies that to subsurface engineering systems. So a few words about, she's a very prolific writer and well-cited also. She's also received several awards, so I will just read them. She, for a PhD thesis, was ranked #1 Outstanding PhD Thesis Award from the Chinese Society of Rock Mechanics and Engineering. A few years ago, she obtained the Director's Award from LBNL, Director's Award for Exceptional Early Scientific Career Achievement. And she was also participant of the US Frontier of Engineering Symposium organized by the National Academy of Engineering. Okay, so she has been, as I said, very successful in terms of fundraising. In particular, she received a couple of years ago, I believe, a big grant from DOE ARPA-E about geological hydrogen production. So that's going to be the topic of our presentation today. So please join me to welcome Mengsu Hu.
Thank you so much, Manuel, for the nice introduction. I'm very honored to be here today, and I really appreciate the opportunity to speak today about our work on geological hydrogen, which was only started about 15.3 months ago. I use this unit as month because this is how fast usually ARPA-E moves. So within this 15.3 months, our team has done a lot of work on the numerical modeling, experimentation, and characterization that build understanding and also some kind of technology toward economic and seismic-safe geological hydrogen. That's the topic that I'd like to share today. First of all, I would like to acknowledge the excellent team I had the honor to work together with that include many, I would say, I'm proud to say the world's best modelers, geologists, and experimentalists. We also have a team of excellent postdoc, PhD students, and summer intern students coming from all over the place in the US. But in particularly, I would like to thank my colleague Carl Stiefel for teaching me so much about geochemistry and reactive transfer modeling, which enables us to work together to solve important problems for geological hydrogen. So geological hydrogen, as you may all know, is a promising low-carbon primary energy resource. Large quantities of geological hydrogen can be produced in the crust through, for example, serpentinization, a water-rock interaction reaction, radiolysis, and deep sea mechanism. The video here shows the world's largest flow, perhaps documented. I'm sorry about the ad. And largest flow of natural hydrogen gas with 84% measured in Albania chromite mine, which is about 1 kilometer underground. And you can see this hydrogen being bubbled through these steams very vigorously. And this is estimated to produce 200 metric tons of hydrogen per year, and which is actually can be very economically potential if such a flask can be obtained everywhere. In the U.S., at the early beginning of this year, USGS released a prospectivity map of hydrogen generation across the U.S. We see this darker blue means more potential. We see this basically across the U.S. There's a large potential everywhere in the U.S. And particularly zooming into California, we see a large regions associated with the California coastline. We see the hydrogen occurrence. And this known occurrence associated with, for example, the Cedars, California, the geysers, a geothermal field, and then some other places very near the San Andreas Fault. And zooming into Minnesota, we see connecting from Michigan, Minnesota, Iowa, Nebraska, and Kansas. This is the Mid-Continent Rift. And also in particular, also another region is the Duluth complex, where there's the abundance of Fe-rich rocks that can be very promising for produce geological hydrogen. So geological hydrogen can be observed from the surface. The figure on the left is showing hydrogen bubble in a stream at the Cedars, California. We see this bubbling coming out. And then we also can observe hydrogen from underground, such as in the Albania mine, and also geothermal wells. Here, this figure shows a 1980 documentation about hydrogen being produced in the geysers. And there they found a correlation between H2S and also H2. And they compare these geysers in 3 regions and found that in the southeast region, there are more potential for hydrogen to be produced. Therefore, my colleague Eva Schell and her team are launching a new project measuring the hydrogen gas from the geothermal wells and try to understand how these are formed and then how can be further stimulated. So geological hydrogen can be categorized as the natural geological hydrogen. As mentioned in previous cases, they have already been occurred and accumulating in the subsurface and rising to the surface. Another type of geological hydrogen is stimulated hydrogen, means generation of hydrogen being engineered at enhanced rate. Despite the differences in the reaction rates or modification of the reservoir rocks, same or similar technologies may be used for extraction of geological hydrogen. The figure here shows a conceptual figure of our ARPA-E project, where we target at a partially serpentinized rock. We target at both natural and stimulated hydrogen at a range of depth with different temperature, pressure, and stress ranges by making use of natural and created factors. So we categorize geological hydrogen into 3 stages, which appear very simple to everyone, but later I'll explain why we need these stages. The stage 1 is to create a network of factors between the injection and production wells. Now, stage 2 is to hydrogen generation, for example, through water-rock reaction. And stage 3 is to extract the hydrogen from the production well. And with these different stages, we're able to design different injection strategies for different purposes. And I have to say, these stages may vary depending on the reservoir conditions. For example, if the reservoir is very permeable, then maybe we don't need a stage 1, or stage 1 can be somehow simplified. If the reservoir is abundant of natural hydrogen, then stage 2 can be somehow simplified. But in most reservoirs, we would expect cases with partially serpentinized rock. That means there are some natural hydrogen can be extracted and also potential to stimulate more hydrogen generation. So serpentinization is the most common mechanism for hydrogen generation. This involves Fe2-bearing minerals such as olivine reacting with water produce serpentine brucite, magnetite, and co-producing hydrogen. These coefficients VW, X, Y, Z are the stoichiometric coefficient which differs based on different hydrothermal conditions. And here, these figures give you the idea about how the rocks are altered before-after reaction. So this is single olivine grain before and after partial serpentinization at 200 degrees C. We see this kind of narrow porous serpentine being formed on the surface of these single olivine crystals. And then further, by using powders of the olivines and having this serpentinization reaction taking place, we see some kind of powders after reaction being covered by fine precipitates, mostly serpentine, those needle-like features. And then after being generated, here shows already serpentinized rock from Lucas Valley Road, California. This is a micro-scale image obtained by Michael Mangas group. The greens are the magnetite crystals, and blues are voids. This perhaps is the first of its kind record of documenting Earth's history of generated hydrogen in the past. But these are not kind of individual pieces. Coming together, this is one example documenting in literature as an SEM image of serpentine, and magnetite as these discontinuous white bands surrounding the olivine. This is obtained from Josephine ophiolite. This clearly shows structures of olivine, serpentine, magnetite-filled veins, and also these veins can go across the boundaries of the grains and also within single crystals. So this motivated us with several questions like, what are the reaction pathways under different hydrothermal conditions? Does olivine dissolution and secondary mineral precipitation occur at the same location and time? Doesn't look like a magnetite precipitate near the olivine surfaces. And then how do different generations of serpentine grow? And how does stress affect serpentinization? To be able to answer these questions, first it's important to look at the structures of ultramafic rock, because fractures and faults are important features affect seismic stability, permeability for extraction of hydrogen, and water availability and reactive surface area for generation of hydrogen. And here these figures shows the same sample collected from cedars as a partially serpentinized rock with olivine and serpentine. You can see these olivine-filled veins shows very self-similar structure from micro scale to centimeter scale to larger scale. And the fractures and faults can be created and altered by serpentinization and mechanical processes. We conducted this Brazilian test and tried to manually induce some engineered fractures. Surprising to us is the new fractures are not just forming along the veins, but they actually propagate across these vein matrix boundaries. This is very encouraging for us to know, because this exposes fresh surfaces for reaction to take place. And further, fractures and faults can be altered by serpentinization. And here shows some example results from Professor Nicolas Espinosa's lab in UT Austin. They conducted these experiments at 200 degrees C and 6 megapascal at these centimeter core samples. And here shows the evolution in 4D of fracture network during serpentinization, 2 weeks, 3 weeks, 4 weeks. Note, these red serpentines are newly formed serpentines, which has been segmented from pre-existing ones. You see these new serpentines are mostly formed and clustered more along these pre-existing serpentine vein filled fractures. This indicates, first, these serpentine veins can transport water to enable more fracture. This also indicates more like water-rock reaction at these interfaces. So the key ingredients for serpentinization include Fe2-bearing minerals such as olivine and water, and the fractures and pores and hydrogen. This involves reaction that includes dissolution of olivine, growth of serpentine and other minerals, and generation of hydrogen, and transport of water, dissolved species, and hydrogen, and mechanical deformation, shearing, volumetric expansion, and chemomechanical processes such as reaction-induced fracturing and pressure solution. And these all affected by and can affect the geometric features. So serpentinization involves tightly coupled processes of reaction and mineral transformation, transport, mechanics, and geometric changes. Compared with geothermal and petroleum engineering, unique challenges exist for geological hydrogen. These are tightly associated because serpentinization involves these tightly coupled processes, and as a result, they affect reaction rate, fractures, and permeabilities, therefore affect the economics of geological hydrogen. They also changes the friction and introduce a modified fractures, modify the shear stress and strength, therefore changing the seismic stability in serpentinizing or serpentinized systems. Diving into details about disciplinary, multidisciplinary, and interdisciplinary R&D topics, here shows some diagram. On the left are the subjects that has been traditionally studied and being tackled in oil, gas, and geothermal field. On the lower right are the ones that are being studied in hydrogen research, and upper rights are the disciplines that needs more research for geological hydrogen-specific problems. And the overlapping areas are the interdisciplinary topics. So the R&D disciplinary topics developed in geothermal and oil gas that can be transferable for geological hydrogen include rock mechanics, geophysics, and reservoir engineering. The R&D topics that covers interdisciplinary research topics are drilling, induced seismicity, reservoir creation, sustainable permeability, meaning injecting proppants, for example, to sustain the permeability in the reservoir for the long term. And also alternative stimulation, for example, injecting chemical components for more stimulation compared with conventional hydraulic or thermal stimulation. And then topics such as hydrogen purification, transport, demand, and utilization that have previously been developed in hydrogen research can be transferable to geological hydrogen research. So with this analysis, we see only most unique topics are reactive transport, chemomechanics, and biogeochemistry. Therefore, geological hydrogen may be a new topic, but it's not like completely new to everybody here. Because of the technologies and infrastructures that are transferable from conventional topics to geological hydrogen, so it actually can cover a range of GRL researches. So everyone here is welcome to contribute based on your background knowledge. And in the following slides, I'm going to show our research that covers these different aspects. The first I'd like to show is hydrogen generation from powders to fractured rocks. So the first attempt of experiments we try to do is, can we generate hydrogen from the lab? So we collected samples from the Cedars, California, and then the Twin Sisters downline, still water. We compared the results by grinding the rock into powders, putting these powders into this batch reactor, and we collected hydrogen gas at the headspace. And here shows the curve of hydrogen generation over time. The red dots are the measured hydrogen, and the blues are the calculated ones. And so these experiments are conducted, particularly for this one, is conducted at 200 degrees C and 16 megapascal. And this gives the rate for the hydrogen generation about 10 to minus 7 kilogram hydrogen per meter cube rock per second. And upscaling to reservoir scale, it can be very, very economically potential. But in the reservoir, rocks are not powders. They have complex features, and the reactive surface area are much lower. So second set of example I will show will involve more complex samples. But before that, in order to understand what are the reaction pathways, what are the ratio of water versus hydrogen generation, and how the minerals are modified, my colleague Carl Stiefel used Crunch and adopted a new thermodynamic database that determines when minerals are dissolved and when minerals precipitate. And using hydrogen being collected from headspace here to calibrate the model, and he derived this stoichiometry, which I call Stiefel recipe. According to this stoichiometry, water hydrogen molar ratio reaches 21. This is actually a very large amount of water consumption. So this is mostly consumed by serpentine. And this also gave the ratio of Fe3, Fe2, which is the indicator of what's the degree of serpentinization. And the spatial distribution of such ratio can also inform the past generation and transport for hydrogen generation. And also importantly is assuming if all the olivines being reacted, then that could lead to up to 46% volume increase. This is actually a very large number. But this is a condition when all the olivine being reacted, all consumed, then generate hydrogen. And this could be the key to drive chemomechanical processes. Now diving into the meter scale core flooding experiment. So here is the same sample. We have these centimeter cores stacked onto each other. These cores have already been serpentine filled veins with natural fractures, and then we kind of induce a natural fracture within each. So they were stacked on top of each other, put into the tube, and sent into this meter scale reactor. So we inject water from the bottom, and then collect the hydrogen water and then separate them in a separator, and then we measure hydrogen over time. This perhaps is the first meter scale flow-through hydrogen generation experiment. It's really more closer to reservoir condition than other types of batch reaction, but it's very, very challenging. The challenges come from because it's very difficult to not disturb the rocks when we try to place in a tube to put some kind of confinement to them. A second challenge is that originally we're trying to measure the volume expansion using water being squeezed out of the system. But because there's water leakage, and such an attempt was not able to be made, so we are having alternative ways to measure that. And another challenge is that there's a long transport length over which hydrogen is generated, which also is common in the reservoir scale. And because of this, there is a complex processes to understand, especially when we can obtain spatial distribution of the aqueous geochemistry and mineralogy over time. So here is the results of hydrogen generation over time. The initial period is the period when it started from July 4th. It's the time when there is not much hydrogen being collected because of the leakage system. Then after we solve the problems with leakage, here is the hydrogen production rate. This is actually very, very, very low. It's a micromole over many days. So this is about 2 orders of magnitude lower than the powders generation, for example. Then we think maybe we can increase the flow rate to see if there's more hydrogen can be generated. After the flow rate being increased 5 times, there's an abrupt increase of hydrogen production. It's about 30 times than before. And after this abrupt increase, we reach the new steady state, and the production rate reaches about 5 times, which is proportional to the flow rate. And so our interpretation at this moment is that this hydrogen generation rate shows very clear transport control in this meter scale fracture core experiment, because water needs to be transported to the surface. Hydrogen needs to be generated, and also hydrogen that has been generated needs to be transported to the top to be collected. But still, what explains the 30 times increase? I leave that as a puzzle. And then here is the summary of all these laboratory experiments conducted at LBNL and UT Austin under different conditions. Each of these experiments has been run for 30 to 90 days. So we actually tested these samples using powders and chips, and powders at stir flow-through conditions. These 2 core, centimeter core samples from CEDARs at UT Austin, and also these 2 fracture core experiments. So here shows that by using powders, the hydrogen generation rate is promising. And especially when the flow is in the system is stirred, that basically transfer from diffusion control to surface reaction control. And in addition to that is the hydrogen bubbles that has been attached to the surface maybe escape away. So it allows for more reaction surface area to be available for further reaction. And then for the intact cores, they show promising amount of hydrogen because the serpentine filled veins are able to enable more reaction to take place. And then the least amount of generation is from the meter scale example because the least amount of reactive surface area plus the long hydrogen transport pathway. So based on this, we have this conclusion that maybe it's more effective to increase the reactive surface area through fracturing, which we call mechanical catalysis, than chemical catalysis to speed up hydrogen generation. Now I'm going to shift to talk about chemomechanical coupling, because this is a system where it's not only chemistry reaction taking place, mechanics also play an important role. The stress can have several effects on reaction. The first is that the values of the stress can affect the thermodynamics of the minerals, and the spatially variable values of the stress can produce gradient for transport to take place. So stress affects both reaction and transport. They can also affect the reactive surface area through mechanical fracturing. And also, because of volumetric expansion, the pores can be filled or even clogged. And also at the right stress conditions, their reaction-induced fracturing can occur. So previously, our team has also explored the reaction rate versus the rate and the extent of volumetric expansion, and also the effects of anisotropic stress conditions and geometric features, including natural fracture and how they affect reaction-induced fracturing. But today, I'm going to be mostly talking about stress effects on reactions. So talking about stress effects on reaction, previously, we have derived this new interpretation of pressure solution as stress-mediated dissolution. Means that at high compressive stress, the dissolution of minerals are enhanced, and it creates a gradient for the dissolved species to transport and precipitates when equilibrium is reached. And here shows the basic figure how this happens. So on the left is at the granular salt, the stress is built up at these sharp corners after the contact. And this high compressive stress starts to dissolve this part of this species and then transport through the porous media. Therefore, this shows the sodium concentration after 20,000 hours of reaction. So this gives the kind of visual idea about what pressure solution means. So this modifies the geometry, mechanical pressure properties at multiple scales in granular systems or interfacial systems. For serpentinization problem, there are two counterparts. The first counterpart is the olivine dissolution. Another important component is serpentine growth. They can both be modified by the stress or normal stress. The question is there a unified thermodynamic description to describe both the olivine dissolution and the serpentine growth mediated by stress? To make this attempt, we first look at this a classic law, which is a function of the free energy that has been developed a long time ago. Here is the rate as a function of the free energy. And then to be able to count for stress effect, we added the stress effect into the free energy that now includes chemical potential effect, stress effect, and then plugging this free energy into this rate, we derived this rate as these several components that includes chemical potential effect and stress effect. This actually looks very simple, but it has several advantages. Our previous formulation for pressure solution derived from the different directions, which which is actually much more complicated. But this one includes the formulation when, for example, when compressive stress is larger, this term becomes less, and then basically it increases the rate for dissolution. On the other side of reaction, for crystal growth, when the stress is higher, and it basically this in total, because the Q over Kp is larger than 1, so it is basically suppress the mineral growth. So basically, this covers for both stress-mediated dissolution and also precipitation. And another case when there is no stress, such a form can be reduced to the case where there's, because this term becomes 1, so it's reduced to stress-free term. And another advantage is this rate is kind of is smooth. So when we implement in numerical form using Newton-Raphson iteration, it can be easily implemented. So here shows this normalized rate over log Q EQ. And you can see that for the rate at unstressed crystals, this shows the rate in decline this way. Here shows when rate is 0 is the chemical equilibrium. And for example, another case we give as an example is that when the stress is 100 megapascal, here shows the rate as a function of log Q EQ, and this gives a different value of log Q EQ at the equilibrium. Is a chemomechanical equilibrium. So this is a new chemomechanical rate law that unifies the description of stress-mediated dissolution and also precipitation. Also important to know that we apply this mineral by mineral. So these different minerals have different molar ratios. It can also be subject to different stress levels. So this allows for to consider different locations for mineral dissolution and precipitation. So then we use this model and consider stress effects on hydrogen generation and transport, mineral transformation that includes dissolution, precipitation, and pressure solution, and volume expansion under different stress conditions. We implemented the formulation into NMM Crunch, which I developed together with Carl Stiefel. And we use this geometry from the Cedars, California, and apply this condition for reactive transport, assuming the serpentine veins has higher permeability than the rest of the rock. And we have the flow-through condition from the left to and the bottom to, and the flow leaving the boundaries from the top and right. And we consider 3 stress conditions: no stress condition, and one case is under anisotropic stress, simulating a depth of 1,600 meters, and another is isotropic stress conditions. Here shows the results of hydrogen gas concentration at early time. Let me show this again. This is very, very early time, up to 24 hours. And what we mostly see is hydrogen gas being generated in the matrix. And comparing with no stress, anisotropic stress, and isotropic stress conditions, the spatially variable stress produce variable reaction rates, and more, the isotropic stress suppresses more of the hydrogen generation because the mean value is relatively larger. And running the simulation to longer, to 100 hours, we see that at this stage, is not only hydrogen being generated, also the generated hydrogen can diffuse into the fractures and flow out of the domain. So there's a mixture of these different processes. And running the simulation to up to 7 days, we see the hydrogen starts to accumulate in the matrix. That is not because more being generated, because there is the continuous generation and also diffusion into the fractures and leaving a boundary. And again, there is less hydrogen being generated due to the suppression of reaction rates by the stress. And different geological hydrogen experts may ask me a question: is this true everywhere in the subsurface? We believe it's possible. There's still hydrogen not being extracted in the porous media just because they can't diffuse out. So this is probably one angle to look at for natural hydrogen. Summarizing the hydrogen flux out of the boundary for different stress conditions, we see the more hydrogen leaving out of the boundary, being generated and leaving the boundary with no stress conditions compared with the stress conditions. Further taking a look at these mineral changes, this shows the mineral volume fraction after 7 days of reaction under anisotropic stress. We see this distribution of these different minerals are strongly affected by the stress distribution. So this is a combination of the stress-mediated dissolution and precipitation and transport, and it's forming these kind of patterns. And if all the olivines are reacted from the beginning, this leads to net volume expansion of 29%. So according to these sets of simulations, we suggest there might be a limited depth window for hydrogen generation to take place because stress can suppress the serpentinization, therefore the hydrogen generation rate. Another effect of stress is to close the fractures in the subsurface. So that's the effects that we didn't really consider. But in addition to that is another important effect. So because of that, we need the modeling to be integrated with characterization for economic exploration and drilling. Now we'll talk about hydrogen generation in the lab and computer simulation considering the chemomechanical effects. Now I'd like to shift it to talk about hydrogen extraction. So the key purpose of our project is to look at extraction of hydrogen and also generation of hydrogen under cyclic injection. Traditionally, cyclic injection has been proposed and developed from small laboratory work to even underground research labs at different scales to mitigate induced seismicity while improving the reservoir performance. The main mechanism for these to work is to lower the breakdown pressure, create more distributed fractures, and reduce the magnitude of largest induced seismicity. And so here is one laboratory's results showing fracture creation under triaxial injection test using continuous injection, cyclic injection with different cycles. And with using cyclic injection, you can see more distributed fractures can be created through laboratory experiment. And so this basically make use of cyclic injection for energy dissipation more effectively in the rock fracturing problems. Now the question is, how does cyclic injection, does it affect and how does it affect hydrogen water flow for enabling more hydrogen being extracted? So we explore this question using cyclic injection starting from a geometry obtained from Oman. It's a famous site. I think Emmanuel's EFRC has intensively studied that site. So this is one image. I wouldn't say this is very representative, but that's the image we chose, which involves dominant fractures and some secondary fractures. So these are the phase configuration, and this is a fracture and the olivine matrix. So we tested the different constant cyclic injection scenarios, and here's a recovery factor. Recovery factor means the mass of hydrogen being extracted compared with the mass of hydrogen being existing in the system. And the recovery enhancement is to compare the relative recovery factor of cyclic injection to constant injection. So here shows these different plots of recovery factor using constant injection and different cyclic injection scenarios. Due to the dominance of main fractures, the recovery factors of all scenarios are over 65%, so easily to extract all hydrogen from the main fractures. But the recovery enhancement by cyclic injections minor is less than 10%. Because the recovery is majorly controlled by these main dominant fractures. But the one important mechanism that we learned from this is by using cyclic injection, we were able to recover more hydrogen from these secondary fractures. So from this, we see perhaps more realistic and hierarchical fracture geometry needs to be considered. So then we use this Cedars California fracture geometry and basically set up a model using this geometry. We tested many different cases for cyclic and constant injection. And here shows the video of the comparison. So mechanistically, by using cyclic injection, this allows a longer shut-in period enables sufficient transport of water. Therefore, they can recover more hydrogen from the secondary fractures. But at a relatively low injection rate, doesn't recover more than 70% of hydrogen from the system. So we increase the injection rate from 5Q to 8Q. And then we were able to recover 80% hydrogen from this fractured media. And then this compared with the constant injection, this enhanced recovery rate by 5 to 30%. This is actually can be very good if this is real for the field. So to test this, we also explore like if the fractures have a heterogeneous aperture distribution, does the cyclic injection work? How much that works? So here shows this comparison between the constant and cyclic injection by using different average flow rate. And by using higher flow rate and more hydrogen can be recovered. And comparing with several cases using cyclic injection, we can see similarly more hydrogen can be recovered from these secondary fractures. These are far from these primary fractures. But if you look at the recovery enhancement, these are not huge. So we think that's because the fracture apertures are secondary geometric features comparing with the intersections of the fractures in a network. So those are the numerical examples. We also want to validate in the lab. So coming back to the same setting, same rock, we did some new sets of experiments. We first conducted initial tracer tests to give us some qualitative understanding of the porosity and permeability distribution. And then we saturate the system with hydrogen. The purpose is to in the hydrogen saturated system, we aim to see how much hydrogen can be extracted from the system. So then first test is to conduct a constant water injection for hydrogen extraction. Then we resaturate the system with hydrogen with the same amount, so make sure the system is comparable. And then we conduct a cyclic injection for hydrogen extraction tests. So these results are fresh from this week. The orange curves are the constant injection, and the blue dot curves are the cyclic injection. And this experiment is still done. The reason is earlier results shows cyclic injection is here and the constant injection is here. We analyzed maybe the H2 injection were not completely exactly the same. So we actually recently just redid the experiment on constant injection, so make them comparable. As you can see, we use, for cyclic injection, we basically use a cycle as 80 minutes, injecting for 40 minutes, resting for 40 minutes, and then, this parameter is beta. And then, so basically, to make this injection volume comparable, its Q is twice as this constant injection. So at the initial time, you can see a much larger amount of hydrogen can be recovered by using cyclic injection compared with constant. Then over time, these two gets closer. So I'm waiting to hear more about this experiment. My expectation is probably just go this way, while cyclic injection doesn't necessarily reach a steady state. So this is still remain to be proven more rigorously to see whether how effectively hydrogen generation can be, extraction can be enhanced using cyclic injection. And then we also conducted reservoir scale modeling using cyclic injection and hydrogen production. So this is 400 by 400 meter using TAF that's developed at Albinel. My colleague Johnny Ruquist and his student conducted this modeling. And they actually designed with this very rigorous schedule for cyclic injection and also cyclic production at the same time. So they are kind of couple effect. So here shows quickly about the comparison between cyclic injection and continuous injection. The reds are the hydrogen gas. We can see by using cyclic injection, more trapped gas can be recovered from this system compared with continuous injection. The reason to design the fracture geometry this way is so that allow us to design specifically like what's the magnitude and intervals of injection resting period we should have for cyclic injection, because we think this is determined by the spacing of fractures and also extent of the fractures. So this is the ongoing work for optimization. But from this, we learned that managing water injection in the reservoir is the key to sustain the generation and transport of hydrogen that can be achieved through cyclic injection. And adaptive control of production while pressure can also enhance the extraction of hydrogen. So then when there's a good combination between cyclic injection and production, more hydrogen gas can be extracted instead of being trapped. So next I'm going to talk about induced seismicity. During hydrogen generation, there are new minerals being formed, and they can modify the stress and potentially inducing new fractures, and they can change the frictional stability. And during the hydrogen extraction, injection of water and production of hydrogen modify the reservoir pressure and stress conditions, so can also potentially change the seismic stability. This is a very conventional study, has been done similarly in other reservoir engineering systems. So changes in seismic stability can be multi-scale long-term effects during both hydrogen generation and extraction. Now, particularly if you're looking at a granular system, here are the chemomechanical processes that can modify the seismic stability. This includes the granular contacts and then granular cracking or subcritical crack growth when the chemistry and the mechanics satisfy. And another important mechanism is a pressure solution would dissolve some of the species away, which doesn't show here. So there's supposed to be a rock here and dissolved here, and you can see this free up the space, allow for grains to be compacted more, shear more, or rotating. And then for serpentinizing systems, because of the volume transfer expansion, that would kind of redistribute the compressive stress and also kind of increase the compressive stress because of tendency of expanding. At the same time, the mineral surface changes from olivine to serpentine would change the friction on the mineral surfaces. So to be able to analyze this process one by one, I propose to use to examine the 3 scales of friction being modified by these processes. So what is 3 scales of friction of granular system? That is the one that previously I conducted 2 sets of numerical experimentation, considering shearing of a spherical granular system and this non-spherical granular system without interparticle friction and with interparticle friction. When there is no interparticle friction, you can see the energy can dissipate easily. Grains can move, rotate, relocate, and then dissipate the energy. What was very surprising to me is when there is interparticle friction, because the spherical particles are packed very tightly, it's kind of initiation of the friction is much more difficult than these non-spherical particles. And after that, then the non-spherical particles start to rotate, giving space for each other to relocate, and finally the kind of reaches this system where you see these force chains. So from there, I propose 3 scales of friction that involve first scale friction controlled by grain packing geometry, and the second scale friction controlled by these individual grain angularities that allow the grains to rotate, which is a resilience to shear. And third scale friction is interparticle friction controlled by minerals and water films. So in the ongoing and future study, my important question to answer is how does serpentinization modify the 3 scales of friction in granular system, therefore affecting their seismic stability? So the last thing, I only have one slide, is the economic potential. I'm sure many people are very interested. So we have conducted these laboratory experiments with different grain settings, different temperatures running from 30 to 90 days, reaching steady state. And then we consider 2 cases using, first case, the Utah Forge stimulated reservoir volume. And second case is the Fervo, a commercial geothermal field stimulated reservoir volume. We consider in both cases, the reservoir rocks are assumed to be already 50% serpentinized. That means another 50% can be used for generating more hydrogen. So using this steady state hydrogen generation rate and extrapolate to 6 months and 12 months in each cases, we see that for every case, if at the scale of a Fervo Cape project, geological hydrogen can reach the economic target of 8 million kilograms per year. And if using the smaller scale reservoir like Forge, the powder case can reach the target. And these 2 cases are not at 200 degrees C are very close to the economic target. But again, this is still very ideal cases. So we're also for meter scale course where we are trying to induce more factors to see how many orders of magnitude we can increase hydrogen generation from this to be able to reach the target like others. Anyway, currently we're still working with ARPA-E to estimate the cost range for each of the cases, but I believe this set a very promising future for geological hydrogen. So to conclude my talk, we learned from our experiment that at UT Austin with this 4D imaging, serpentine field fractures can provide pathways for water transport and reactive surface area for generation of hydrogen. Increasing reactive surface area through fracturing could be much more effective than catalysis to speed up hydrogen generation. There we call fracturing is the mechanical catalysis for hydrogen generation. We developed a new unified chemomechanical rate law for both pressure solution and stress-mediated crystallization. We learned that stress can modify the spatial distribution of hydrogen generation rates and transport, therefore affecting the hydrogen production. Through our results, we learned that there might be a limited depth window for hydrogen generation to occur. Therefore, we need modeling to be integrated with characterization for economic exploration and drilling. We learned from the cyclic injection versus regular injection cases for hydrogen extraction that distributed fractures are preferred for economic extraction of hydrogen. And also, it's very important to develop good injection and production strategies to enhance the hydrogen production. Changes in seismic stability can be multi-scale long-term during both hydrogen generation and extraction. And we call that multi-scale and interdisciplinary research across academia, national labs, and industry are needed to accelerate the development for geological hydrogen. Thank you very much for your attention.
So the floor is open to questions. Paige?
Thanks so much for a really interesting talk. I'm an environmental engineer, so I come at this from a different perspective, but I wondered if you knew what the impact of water pH was on the dissolution and hydrogen generation reactions.
That's actually a very good question. So we have the plan to increase the pH. That's our literature report. Many reporting increase in the pH can increase the hydrogen generation rate. So that's actually our next step to explore such effects fully about if there is an optimal pH for H2 generation.
Okay.
Yeah.
It might be interesting to decrease it too. If you have CO2 in the
Yes.
water, you know, you
Yes.
can like
Yeah.
nail two birds with one stone.
Yeah.
And then I wondered I know with fracking for natural gas recovery, they add a lot of chemicals to the water.
Yes.
And I wondered if that would happen here as well, and what impact that would have on hydrogen consumption by microorganisms, and then also the chemical production of hydrogen if you've got, different surfactants or oils, things like that in the water.
Well, I have to say you have very good understanding of the field. This is very complicated. So on the fracturing part, people do injecting acid to create more fractures or even more distributed fractures or more distributed porosity within a single fracture to achieve such goal. For example, attempts has been made for geothermal systems. And in hydrogen assume that will be similar effects can be achieved. And then for the generation part, our team hasn't been doing this, but other teams are exploring a different solution chemistry to enhance hydrogen generation, which I think, for example, if I remember correctly, adding nickel can speed up hydrogen generation, but I don't know if there must be some other different kind of chemical species can be added that can speed up hydrogen generation. In terms of consumption, there is a report bioconsumption is a very major mechanism that takes away that's very important for the economic side for hydrogen production. The question is at what speed microbiology consumption occur versus hydrogen generation can occur. At the right biochemical conditions, maybe hydrogen generation can be stimulated. This goes to another direction, biogeochemical hydrogen generation. But consumption is the one that we don't want. So I'm curious about the temperature rate of bioconsumption, which I think hasn't been reported so much, but experts like Alexis Templeton and there's a professor at University of Minnesota, Duluth, they have been studying such topic intensively. So I think those are all very, very important questions for geological hydrogen.
Sorry. Go ahead and then we'll read the question after that. Go ahead. Sorry.
Thanks. Hi, Mengsu. Nice talk. Very interesting results. I have two questions.
Yes.
First, I saw you in your numerical model.
Yes.
You have this temperature.
Yes.
That's one of the parameter settings.
Yes.
Do you consider the thermoelastic stress, or overall, if, for example, if you inject like a fluid that's cold, do you consider the heat conduction and its induced thermoelastic stress field?
So far, we haven't considered that. But for the fracture part, we actually have the design of lowering the temperature for effectively creating more fracture. But for the hydrogen generation, for example, case, the temperature effects is mostly counted for the thermodynamic database. So
I see.
How it affects the reaction rate.
Yeah, I think it might be a good direction to go with this thermal coupling as well. I mean, it will be like a thermal chemo-mechanical coupling
In
the bottle.
of fracture creation, I agree, yes.
And also, have you considered using propellant?
That's another very important question that goes to basically sustainable permeability in a reservoir. I believe there are many important questions that goes for from creation of fractures to longevity of the reservoir, longevity of propellant itself. I think yes, for the longer term, those are all important questions. If geologic hydrogen are basically becoming really an important topic that industry and academia are all interested to explore, I think that's really excellent direction to go.
I have a feeling that using propellant might be very effective in terms of sustaining or increasing this reaction.
I agree. Yes.
Thanks.
Yeah. Thanks.
Charles?
Do I need to? Yes. Press the thing. No. Just say something. Geologic hydrogen obviously invites a comparison with fracking that's been used in the petroleum industry. But it seems that in the mechanics, one of the big problems is pressurization and the potential for short-circuiting. You know, when you cool the rock, you're going to increase the aperture and so on. But that is not, I think, a mechanism that's very significant here. Am I right?
I think thermal short-circuiting, I think that's actually right, because, for example, in geothermal, thermal short-circuiting is a big problem for geothermal to be economic. For geological hydrogen, similar. So you can see that when you have this kind of dominant fractures, we can't get all the hydrogen out. That's basically very similar phenomena to EGS systems, even though the fluids are different.
Okay. And if I may ask one other, I see that you get most of your funding from DARPA.
Yes.
And yet DARPA, I suspect right now, is under some stress for its own funding.
Yes.
Is that affecting anything for you?
For our ongoing project, no.
No, okay.
And DOE, different offices are also actively thinking about geological hydrogen. But above DOE, there's another layer. Maybe, we can.
There are a couple of questions from online. So, which one is it? The first one? Yes.
One encouraging thing I'd like to share is, if this is still going forward, DOE is putting together a roadmap for geological hydrogen. So we were asked to be one part of the team led by Unreal. So hopefully it's a go forward. So we will be able to deliver a compelling roadmap for geological hydrogen.
That will go to include universities,
So far, I hope to. I will try my best.
Okay, let me read a couple of questions from the online. So, the question from Hain Wang: how are the rate and frequency of cyclic injection designed in the experiment and simulations?
Sorry. The frequency of cyclic injection.
The rate and frequency of cyclic injection designed in the experiments and simulations.
So, in a simulation, basically is trial and error for now, because the best performance depends on the interplay of flow and geometry. So it's trial and error, and hopefully in the future, when we have enough case studies, we will be able to use AI for the optimal solution. For the experiment, that's interesting. We look at the tracer test, which we don't understand, which I showed Emmanuel this morning. The tracer test gives these kind of patterns up and down. That somehow gives us what's happening and not happening. So then we go for some kind of these pattern changes, and then we say maybe this is a good starting point for to design injection resting period. But you can see for meter scale, 40-minute injection, 40-minute resting is very long. So I'm expecting if we reduce this injection resting period to like 10 minutes, cyclic injection will behave better. That's my guessing, but we need to test the data.
Okay, so let me go to another question. Can you explain a little bit more about the tree-scale friction? Are the figures obtained from simulation or experiments?
Three-scale friction, I like this question. This is my passion, one of my most passionate topic. It's very, so for interfacial friction, you have this, it's very straightforward. You have these hierarchical geometric features that controls the interfacial friction. You can even plot a single entrance line given the geometry by using, for example, new contact model that I developed myself. But the granular system is different. They basically consist of many individual particles. And the first thing that we observed from this numerical experimentation is to enable shearing to occur, the first thing is to break through these wavy lines of packing of the particles. So that is the first scale of friction that I propose. The second one is after you break that is the granularity. Granularity and rotational grains basically brings the resilience to shear. That's the second scale. And the third scale is onto each individual surface of the minerals. this friction is basically governed by the mineralogy and also water films. That determines the individual friction behavior of the minerals. So these are the 3 scales of friction. And how they are going to be modified. For example, during serpentinization, volume expand. Your stress distribution would be either your compressive stress in the system will be built up in the tightly packed system, or in a loosely packed system, your grain may needs to like rotate or move to be able to release that kind of built up stress. And at the same time, your friction is likely to be reduced from olivine to serpentine. So those are the effects particularly can affect in the seismic stability in a granular system of serpentinizing rock. So those are the topics I'm currently exploring.
All right, thank you so much. So please join me to thank Mengsu again.